Okay, so total tangent. I remembered a cool video that I had on my computer that I wanted to show all of you, and this relates to this slide that I showed you yesterday. And somebody just asked me a question about this, so I thought I would show you this video, where we talked about how flames can induce really strong flow fields. So the flame basically makes its own flow field. And I had talked about how that can cause boundary layers to separate yesterday, or how they can swirl flows that can cause vortex breakdown in front of the flame. They can cause triple flames to propagate faster, which is why you have that square root of density ratio effect on triple flame speed that I just very quickly showed you. I also had mentioned they lead to flame instability, that flames will spontaneously develop wrinkles. So what I want to show you is kind of a nifty little video. So what's happening here is, so if you remember this picture that I showed you yesterday, assume I have a uniform velocity approach flow. And remember we had said that if you get a bulge in the flame, it's going to cause the approach flow to decelerate, which is going to cause this bulge to grow even more. Right? So this part of the flame is going to go shooting out into the reactants at a velocity which is faster than the flame speed, and it's because it basically changes the flow field in such a way that, in the same way, this part, the flow accelerates and pushes this part of the flame back. So what I want to show you is a video of the Darius-Landau instability developing, but there's one big difference between this picture, which this picture is where the approach flow is nominally the same as the flame speed, so the flame is nominally steady. I'm going to show you a video where this flow is uniform and the flame is propagating left to right. So what's going to happen is these velocity vectors will be 0, but what will happen is you'll see these velocity vectors. Now, if I move in a coordinate system moving with the flame, these velocity vectors will actually go in this direction. So you'll see the flame actually inducing a flow field in front of it that's pulling the flame forward, and inducing a flow field at the concave part that's pushing it back. Where'd it go?
I think it's open.
Where is it?
Just second one next to stop.
Okay, so start it out. Okay, so this is PIV seed particles. Flow is nominally stationary. Flame enters at the top right. The flame is going to be moving down. And from what these PIV seed particles are doing, you can start seeing what the flow is doing. So look there first. See how they're nominally stationary, but then at that concave part, they start rushing into there, right? And then the same thing, if you watch on the leading edge, can't see it, darn. Okay, never mind. Well, you can see, I wanted to show you how it's sucking the flame forward on the front end, which is what's going on over here, but the field of view isn't right. But you can clearly see what's happening here, how it induces a flow field to push that part back. But anyway, that's what leads to flame acceleration in channels, which we were just chatting about, is that the flame induces its own flow, and the flow pulls the flame ahead due to this flame instability. Okay. Okay, I want to now talk a little about flame stabilization and shear layers. And what I'm gonna give you a bunch of ideas, but I'm not going to give you kind of the answer, because I'll just tell you that we don't understand why flames blow off. And it's much more complicated than the simple blow-off descriptions that you'll see in combustion textbooks for Bunsen flames. The world is a much more complicated place. We don't even understand really some of the velocity scaling for flame blow-off. So there's a lot of interesting things going on. So I'm not going to give you the answer, but I think hopefully I'll give you a couple ideas for how you can interpret real-world phenomenon, because I think, if I remember correctly, several of you are working on this type of problem. So let's talk about stretch effects on flames that are stabilized in shear layers. Now, it seems pretty intuitive. If the local stretch rate exceeds cap extinction, the flame will locally extinguish. Well, all right, that's fine. But so kind of a couple questions pop up. First of all, what's kappa extinction? Because in reality, the real flame will be maybe a little bit lifted. There'll be a little bit of dilution of reactants and combustion products. And so what's kappa extinction is an interesting question. The next thing, if the flame, let's suppose it locally extinguishes, does that mean it blows off? Or rather that the flame just sort of lifts a little bit, but then it stabilizes from that point downstream? Or what all happens? But I think overall, if you look at data, it seems pretty clear that you can scale blowout limits with kappa extinction. I'm not saying that I fully understand why, but if I go make a bunch of measurements and then I go do a detailed chemical kinetic calculation of kappa extinction, I can scale how the blow-off limits will change with things like flow velocity, or with hydrogen fraction in the fuel, or equivalence ratio, or preheat temperature of the reactants, or things like that. I can get kind of a gross scaling. That doesn't say that I don't answer all the questions. But let's dig into this question a little bit more of what's really happening in the shear layer. So as we said, in a high-speed flow, although you locally have a low velocity in a shear layer, you can get flame extinction because the flame is stretched. And so presumably the amount of stretch the flame can withstand is limited by that extinction stretch rate. And the strain rates in shear layers are huge. So for example, if you have a 50 meter per second jet and a 1 millimeter shear layer thickness, then your flow strain rate is on the order of 50,000 inverse seconds. That's a really big number. Okay? And just to calibrate you, if we look at the extinction stretch rates, I showed you a whole bunch of different extinction stretch rates before. Where'd that go? These are kappa extinction values for methane, hydrogen, air. You can see they're ranging between about 1,000 and 10,000 for these room temperature reactants. These are some numbers. You can see 15 bar, I'm getting up to extinction stretch rates on the order of 60,000, but at 1 bar, I'm extinguishing way down around whatever that would be, a few thousands. So the flow strain rate that flames are seeing are really big in modern high-speed combustion systems. So if you just said, well, let me just try to use that to predict flame extinction, that just wouldn't work. This number is much greater than typical extinction strain rates. But that raises a question: how is flame stretch related to flow strain in a shear layer? So this goes back to the point that I made where I showed you that expression for stretch rate. And I said there was that one expression that explicitly shows the relationship between flame stretch, which is a surface defined quantity. It's the stretch rate of a surface. How is that related to flow strain, which is this volumetric deformation of fluid type phenomenon? Well, okay, what if we go back to how do you get flame stretch? Well, you can have flame curvature, but you also have this you can have unsteadiness in the flame and flow, but you also have hydrodynamic strain. And I apologize, there's a little bit of a nomenclature disconnect here. This is this is kappa S. Is that what I called it before? I forgot. This is that N dot S dot N plus del dot U term for the stretch rate. I called it, let's see, kappa S and kappa curve. That's right. So this is the kappa S term. And so what I want to do here on the next couple slides is just real quickly talk through how does basically dUI by dxj, which is your flow strain, the deformation of the flue, how is that related to flame stretch? And so again, reminder, the fluid strain rate is given by this tensor. So what I want to do is, this will be my geometry. So imagine this is the metal or the combustor wall. My flame is attached or nearly, coming close to the wall. I'm going to get this edge flame right here, and it's going to locally extinction when it gets too close to the wall. I have the flow coming in this direction. The flame is going to be spreading at some angle theta with respect to the flow. And what I can do is, I'll just do some math. Okay, so I'm going to skip the math for you, but let me just take this expression and let me just chop it apart, decompose it into different components. And by the way, my coordinate system is going to be z is the axial direction, x will be the transverse direction. So if I do that, the expression for kappa S looks like this. And I end up with basically kind of two categories of terms. One I'm going to call the normal strain contribution. The other is the shear strain contribution. So the normal strain is how is the axial velocity changing in the axial direction. So in other words, if UZ is the velocity that's in this direction, how is UZ changing in the direction of flow? So this is the flow in bulk accelerating or is it decelerating at the flame? Well, what would cause a flow to accelerate or decelerate? Well, usually flames are stabilized at points of rapid expansion. So it would be very typical for the flow to be bulk decelerating as it's entering a combustion system, right? I don't care what your geometry is. Let me just draw a picture. You know, so if you had, let's just say, a dump combustor that looked like this, here's the flame. The flow is transitioning from this cross-sectional area to that cross-sectional area. At least nearby, it's going to be bulk decelerating. Obviously, farther downstream, it's going to depend on the gas expansion ratio and the area ratio. But right in this vicinity, it's going to be generally decelerating because of the expansion ratio. Not always, but that's what I mean by normal strain. And remember, what's normal strain? It's taking fluid elements. You know, if I take a fluid element, a Lagrangian fluid element, and it transforms into that would be normal strain, right? Where I stretch it but push it. Whereas shear strain would be if I take a fluid element and I do that to it. But anyway, it just turns out that you can nicely decompose that expression for flame stretch as you just start evaluating the expressions. There's this term, and then you also get this term, which is shear strain. So you'll notice this is du x by dz. So what we're asking now is the velocity component in this direction, how much is it changing in the flow direction? And then this term right here, this is the big term, right? This is duz by dx. That's the term because uz is going to go to 0 at the combustor wall in the boundary layer to its free stream value. Duz by dx is presumably going to be very high. So of all the terms here, duz by dx is probably an order of magnitude, maybe even 2 orders of magnitude bigger than every other gradient in the flow, the shear straining velocity term. So let's talk about that. How does flow straining lead to flame stretch? In particular, how does shearing flow straining lead to flame stretch? Well, it's actually quite simple. So what I'm going to do is, just to illustrate the idea, here's my flame, and I've tried to illustrate shear by having my velocity vectors increasing. Okay, so low velocity, medium velocity, high velocity. Does everybody follow? And remember, what is flame stretch? Ultimately, flame stretch is the change in velocity, the change in tangential velocity along the flame, right? So if I take this velocity vector, I'm going to decompose into a normal and tangential component. Normal and tangential, normal and tangential. So what's happening to the tangential velocity field? It's increasing, right? So what's the stretch rate? Positive or negative? There's the answer. Positive, right? Yep. So in this case, shear strain, the shearing distortion of fluid elements will lead to positive flame stretch. You know, the equations will show it, but I want you to kind of get an intuitive feel for it. And again, I would encourage you, if you're working these problems, just draw the picture. Take a picture, take the flame, take the flow, decompose it into the tangential velocity, and you can see the tangential velocity is increasing in the flow direction. Now, if you actually evaluate this expression, it looks like this. And you can see I'm just going to neglect, where is that term? I'm going to neglect that term because it's going to be so much smaller than that term. But it's basically nx times nz. So this is flow strain, and this is the term that relates flow strain to flame stretch. So nx times nz. So you might say, well, you know what? Just for starters, I have a really high velocity flow. Let's just assume that theta is 0. Let's assume that the flame is almost parallel with the flow. Well, if theta is 0, what's the flame stretch rate? Zero, right? Two ways you can see that. One is, and that would be kind of a limiting case where the whole reason the flame is stretched is because the flame is poking out into the flow, that different parts of the flame are seeing different velocity fields, right? But you got to have an angle on the flame in order to do that. So in other words, and what that also shows you is say, well, let's assume that the flame angle is just small, but can I get away by just assuming theta is small? But in fact, it turns out that if a difference between theta of 1 degree and theta of 2 degrees, both small numbers, gives you a difference of a factor of 2. So it's really, really sensitive. And that you can also see that because it's in x times in z. That in x, if theta is very small, in x is going to be small. Excuse me, in x will be close to 1, but in z will be small, be proportional to theta. But anyway, so what you can see is it leads to positive stretch, shear does. But from what I've just shown you is that you can see that the stretch rate's a really sensitive function of the flame angle. Again, if you don't know if the flame angle is 1 degree or 5 degrees, which might sound close enough for lunch, that's a factor of 5 difference in flame stretch rate. Okay, so anyway, that's this term right here. So that is how shear is leading to stretching of the flame. It's because the flame is poking out into higher and higher velocity regions of the flow, so therefore the tangential velocity that it's seeing is getting higher and higher as it's sticking out into the core flow. What about this term right here? Well, let's assume that the flow is in bulk decelerating, that you're going from the high velocity jet flow and it feels the area change, it feels the back pressure, and it starts to slow down. So let's just assume that. So what I've done here is I've neglected the boundary layer just to keep life simple. I have a bulk decelerating core flow. So I have a bunch of velocity vectors, and as you move farther downstream, the velocity vectors are smaller, then they're smaller, and then they're smaller. Okay? Anybody have a question about the construction? So what you can see is, so what I'm interested now is what's the velocity at the flame. So the velocity here, I'm going to decompose it into that's the velocity, but I'm going to decompose it into the tangential and the normal component. The velocity there, tangential and normal, velocity there, it's a tangential normal. So what's happening here? It's negative, right? So the component tangential to the flame is actually decreasing along the flame. So decelerating bulk flow is actually leading to negative stretch. So what that shows you is this kind of flow straining, at least if it's decelerating, this would be an accelerating flow strain, I guess. But a decelerating flow strain is actually going to translate into compressive stretch of the flame. So if I put all this stuff together and I basically try to calculate it, I have a whole bunch of math here. I don't know, how ready is everybody at 10 to 5 to do math? So we'll just soldier on here. So if I have a high speed flow, then the velocity is going to be much greater than the flame speed, which also means that the flame angle theta is going to be really small. Okay, so if I'm just going to do some quick asymptotics, the in x, the normal of the flame in the x direction, that's going to be equal to -1 plus something of order theta squared. I'm going to neglect the order theta squared, and I'm just going to approximate in x by -1. In z will equal to first order equal theta in radians, plus a term of order theta cubed. Let me neglect that. Let me also assume that this dux by dz is much smaller than duz by dx. That's a decent approximation. So what that leads to is my shear term is going to approximately look like this. Theta times duz by dx. My normal term will equal duz by dz. All right? Let me jump ahead. You know, when I make slides, I have one way of presenting it, and then when I start talking, it just seems much more intuitive to do it a different way. So let me just jump ahead now, and let's go to slide 66. So what's the total flame stretch, right? So that's going to be the sum of those two terms, right? duz by dz plus theta times duz by dx. Well, we just said this term is really big. Theta is small, so I'm taking a big number, multiplying it by a small number, which is always hard, right? When you're trying to estimate a big number times a small number, is the product going to be a big number or a small number? Well, 1,000,000 times 0.1, that's a big number. 100 times 0.0001 is a small number. So it's a dicey business, and I just showed you that if you don't, since it's a direct function of the flame spreading angle. What else do you see here that might make estimating flame stretch rate's really tough. Remember, this term was positive. That term was negative. And I don't know about you, but I never like to add numbers of opposite sign, right? What happens when you add numbers of opposite sign? You have uncertainty amplifiers, right? I have an uncertainty here, I have an uncertainty there, and I just amplified my uncertainty. And so, so for example, let me just do an extreme example. Minus 99 plus 100 is equal to 1, right? Suppose I have a 1% uncertainty. So, oops, it's minus 99 plus 101. Well, the answer to that is 2, right? So, a 1% uncertainty in the input gives me a 100% uncertainty in the output. That's a 100x. That was obviously an extreme example. But the point is that these two terms, we have data. I'll show you data in a minute. These two terms are actually of similar magnitude, and because they're opposite sign, that I'm left with a very uncomfortable situation that I'm going to have to tell you that I don't even know if flame stretch in a shear layer is positive or negative. Because I have two terms of moderate amplitude. And what that tells you is a relatively small change in either of these could swing the flame stretch rate from positive to negative. And so you have a couple things. And I think this goes back to the fact of why today, the state of the art, we can't predict blowout. We can't predict when flames will and will not extinguish in shear layers. And I think really it goes back to this equation, is because you're adding two terms of opposite sign, and the one term, you take the biggest term of all, multiplied by the smallest term of all, plus a term of intermediate sign. So that makes life pretty complicated. Let me now, so if we go back to this, so let's think about scaling these terms. How do we scale these two different terms? So let me go back now. So I just backed up to slide 64 and think about how are these terms going to scale with velocity, how are they going to scale with flame speed and things like that. So here's kappa shear, and we just said it's going to scale as theta times duz by dx. Well, how's theta going to scale? Presumably, theta is going to scale as the ratio of the flame speed divided by flow speed, right? So as the flame speed drops, theta gets smaller. As the flame speed gets bigger. So we'll use this scaling for theta. How is the velocity gradient term going to scale? Well, let's scale that as u divided by the shear layer thickness, delta shear. So in fact, I skipped a step. So in these notes, let me just fill in that step. So if we say it's theta times duz by dx, if theta scales as, what did I say? Flame speed, sd divided by uz. Shear layer, presumably that's going to scale as uz divided by shear layer thickness. I'll just call that delta shear. What you end up with is sd divided by delta shear, right? Actually, the velocity cancels out. Well, that's interesting, you might say. You'd say, so what you're telling me is that the stretch rate that a flame sees in a shear layer stabilized flame is independent of velocity. That's a pretty interesting observation. However, like I said in the notes, in reality, shear layer thickness themselves is also a function of velocity, right? If it's a square root of Reynolds number, it'd be a square root of velocity effect. But what that shows you is just this, the ability to scale what stretch rates are in real flames in this canonical geometry. And this kind of baffles me that we don't know more about this canonical geometry. It's flame stabilization and shear layers. What's the stretch rate? Well, you can see that you get this non-intuitive scaling for velocity. And in fact, the shear layer thickness, particularly for a turbulent, you see you'll get a different scaling if the boundary layer is turbulent versus laminar, right? That a laminar shear layer scales as square root of u. And I can't remember what it scales like for a turbulent. And it also is going to be dependent whether you're on the viscous sublayer or in the inertial, or in the inertial regime of the turbulent boundary layer, right? So Now, if you look at the stretch from the normal stretch rate, the stretch induced by the normal strain, that's duz by dz. Well, how's that going to scale? That's going to scale as uz divided by some characteristic length scale, probably like the diameter of your combustor. So that's going to scale as uz on L. This is a pretty traditional flow time scaling approach for stretch rates. But what you see then is what you're doing is we're adding, if we go back to this equation, this term scales as uz on L, where L would be a kind of a overall jet diameter, let's say, plus a term that scales as SD, flame speed, divided by a shear layer thickness. So these two terms, again, trying to add them, life becomes pretty complicated, pretty interesting pretty quickly. Anyway, and what I have on this next slide, slide 67, that just shows, we've in some other results, we've actually gone in and measured them. And basically what our data shows when we've done it is this term dominates really close. So let's just say here, that term dominates, and as you move farther downstream, the shear term dominates. So anyway, that's just one kind of point, trying to connect back flame stretch to flame stabilization. And I think a really interesting problem, like I've said, for going forward is just trying to better understand what real flame stretch rates are and how they scale for real flows. Did somebody have a question? Okay. The other thing I want to just talk about, another topic, sort of jumping, but on a related topic, is in addition to flames being stabilized in shear layers, where there's high stretch, almost always there's also recirculating flow at the same time. So for example, if you have a bluff body, the flame is going to sit like this, but you actually have backflow, you have recirculating flow back here. And so what that shows you is what's a canonical problem to model this. I have reactants and I have a flame, and on the back side I have this stagnating hot products. This is actually the reason why I showed you some of those calculations for a stagnation burner where we had reactants stagnating against hot products. Some people have suggested that that's a useful model problem or canonical problem to understand what's going on sort of in this stabilization region. Because in reality, it's not reactants stagnating against reactants, or it's reactants stagnating against hot products. And also, that point that I made earlier about extinction is there's always a little bit of a dead space, right? The flame there's a few millimeters, and so there's a little bit of contact. You know, some hot products are coming back here. And so just what the composition is and what the temperature is at this point is an interesting question. You know, here, this would be another picture of a backward-facing step. You have recirculating flow, a swirling flow, and so forth. So just what is this effect of, we know that flow recirculation has an important effect on flame stabilization, but just really kind of coming up with a nice science, physics-based description of how that's modifying the answer, I would say we're not there yet. That's a really interesting problem to work on. And I just repeated this slide that I had here. Let me just say a couple more things about blowout and flame stabilization. It turns out that life's even more interesting than some of the things I've talked about. And so if you came to this class to get answers, I'm afraid I'm not giving you answers, but I'm leaving you with questions that life is interesting. It turns out that when flames blow off, you might, a mental model for blow off could be the following. I have a flame. Let's just think about this flame. I have a flame, approach flow. I've just learned how to calculate the flame stretch rate here, even though you've told me it's complicated and I'm adding a number of opposite and negative sign. But let's just assume that I go ahead and I figure that out. Hypothesis: when the stretch rate that the flame sees is bigger than the extinction stretch rate, poof, flame's gone, and that's blow off. Well, if you actually look at what flames look like as they start to blow off, blowout is really not in a single event, it's really a process. So when we actually look at blowout, it looks totally different. Now that we have all these awesome high-speed cameras and high-speed diagnostics, life is just a whole lot more interesting than you might expect. So here I have, this is a paper we wrote in 2007 for a bluff body stabilized flame, close to blowout. And what you can see is happening is you start to get holes in the flame. See these holes moving downstream. There's another hole, there's a hole. But I don't know, somebody tell me, what jumps out at you about where these holes are or what they're doing? What was that?
It's convecting at a constant velocity.
Mm-hmm. Yeah, so you see the hole, it forms, and then you watch it, and you can see it convecting downstream. You see this thing right here. There's another hole. There's another hole. What else? The thing that jumps out at me is, where is the highest stretch rate going to be? Right near the bluff body, right? Massive strain rates, massive flame stretch rates. But the flame doesn't extinguish there. Why not? Probably it's not extinguishing because of what we were talking about here. Is there some recirculation? So if you calculate the extinction stretch rate based upon sort of bulk average approach flow, that's probably not the right stretch rate, at least in this region, because the flame is really being influenced. In contrast, probably downstream, it's probably the right extinction stretch rate. So what's happening is the flame can actually hang on to a stretch rate that's much higher than you might expect based on bulk average properties right here. But when that stretch rate starts to get to a point where extinguishes downstream, you get a hole. And that's what, we can see that here. We see this hole happening. So that's one kind of observation. This is another picture. This is some line of sight images of a flame. This is really close to blow off, and you can see these holes forming. In fact, you'll see here, the only thing that's left is the flame right in the back side of the bluff body, but the whole rest of the flame is gone. So what you can see is happening is, let me just go back to my little simple mental model that's I'm saying isn't happening. A simple mental model would be flame extinguishes here, then this part of the flame just goes poof and it's gone. But that's not what we see. We see this part of the flame hanging on, and we see extinction happening down here. In fact, I can tell you that what will happen is, as I get closer and closer to blow off, is more and more of the flame is going to be extinguished downstream. But the flame can always hangs on right here. Okay? So in fact, where does extinction happen? It doesn't happen here. It happens down here. You can see that in these images here. For example, the flame is almost completely extinguished downstream. It's just hanging on. And presumably, it's that product recirculation is just reigniting it and keeping the flame on. So what we see is, when we actually look at blow-off, like I said, blow-off is really not an event. It's a process. So we can think of, we've suggested that there's really kind of 3 stages to it. The first is, flame looks like it always did before, but it just every now and then you get these local extinction events. We call that stage 1. And like I said, presumably what's happening is the local stretch rate is exceeding the extinction value at that point. It pops a hole in the flame. Well, as you can probably imagine, if you really, like for example, these images down here, you really start to disrupt what the flow field looks like when the flame is mostly extinguished, and then maybe all of a sudden, you go from there to there, all of a sudden, bam, the whole flame is back. You can imagine that's creating a whole lot of unsteadiness. And so what we'll see in stage 2 is the flame, the whole flow field, the whole flame, it just starts to look fundamentally different. In stage 1, it's sort of, if you kind of squint or if you have a low-speed camera, you wouldn't even see it. It would look the same as when it's healthy. In stage 2, you'd say, yeah, maybe it starts to get noisy because of all the extinction reignition, or it just starts to look really, really different. So what's happening there is that extinction is causing large-scale changes in the whole wake and recirculation flow dynamics. So let me back up to this picture. So this nice, pretty picture of what's happening is no longer happening when you move into stage 2. And as you can probably imagine, if all of a sudden this whole back end of the flame is gone and you're dumping, you got you're pumping hot products in right here and all this cold stuff right there, and they're meeting and mixing, and you got density changes, and that affects vortex dynamics. And then all of a sudden, the flame is gone, blow off. So one of the things that we've suggested is what our blow-off scalings do. For example, I mentioned before that, well, if we actually take real blow-off data and we calculate, let's say, a Karlovitz number, a flow stretch rate, or we estimate a flow stretch rate and we estimate a flame extinction, that we can actually correlate the data reasonably well. But what I've just told you is, but that's not what's really happening in the flow. What is probably happening is that Dom-Kohler number scaling approaches are Karlovitz scaling approaches, basically a fluid mechanic, a flow stretch time, flow straining rate normalized by a flame extinction stretch rate. Probably what those are doing is they're describing stage one. So sort of all the classical, if any of you are working at Blowout and you look at the classical scalings for Blowout, what's probably happening is those are not scalings for Blowout, those are scalings for stage one. Those are telling you where you're starting to get extinction in the flame. The reason they work is because stage one is correlated with blow-off, right? You get a healthy flame, then you get a flame with holes in it, and then you get a flame that really looks crazy and large-scale disruption, and then it's blown off. So what I'm doing is, let me just think about this. Let me draw a picture here. Let's suppose I'm marching in equivalence ratio down. So I'm doing a blowout measurement by dropping equivalence ratio. What'll happen is, let's just say right here I hit stage one. And I keep dropping it, and I hit stage two. And then at some point, the flame is gone. What I'm suggesting is all these extinction ideas are really what they're doing is they're telling me what's happening here, where this occurs, where I start to initially get holes in the flame. But because that and that are presumably correlated, so for example, if I now double the velocity and I repeat the experiment, these things will move, but I still get the same idea. Because these are correlated, that's probably what's driving the success of a lot of these sort of classical scalings you'll see in the literature. But I just want to emphasize that if you think about what's really fundamentally happening on the ground floor as flames are blowing off, I don't think a lot of these blow-off scaling approaches are really telling you what's happening. They're just telling you when you're starting to get extinction. All right, I just threw a really deep thing at you all, but yes, sir.
I was just wondering if you could comment, if possible, on like emissions of CO and unburned hydrocarbons from stage 1 to 3.
Yeah, so what will happen is you'll start to see the CO take off in stage 1. When you hit stage 2, don't be behind it because you'll die, because the CO emissions will be in the thousands of parts per million. Clearly, something will be wrong. Yep.
I have a question. So you said that there's always going to be a bit of a flame just downstream of the blood body. If that's so, why can you not reignite it? And why did it just completely blow off?
Yeah, that's a great question. So what causes stage 2 to go to stage 3? We don't know the answer to that. If something happens, it's stochastic, because that for some reason all of a sudden the flame does not reignite. But yeah, it's a great question. Yeah.
Is it possible to control the onset of stages? Say you figure it was at stage 1, would you be able to prevent it from going to stage 2?
Well, that would give you that you could use that as a precursor. So usually flames will tell you they're about to blow off before they blow off. It's not just like falling off a cliff. So this is a very standard approach using real combustion systems. Many of them, this unsteadiness, this little extinction and ignition that you start to see in stage 1, that makes noise. And we'll talk about that tomorrow when we start doing acoustics. That makes sound, but you can hear it. So like commercial combustion systems, they know when you start hearing certain types of sounds, turn on a pilot flame or start increasing the equivalence ratio or something like that because you're near blow off. Any other questions? Let me, so that's shear layers. I think, so let me just highlight, I'm going to repeat myself, but let me just say it one more time. What I think is happening is that flame stretch, really important concept because it tells me the conditions under which I do and don't have a flame. Edge flames, that tells me once flame stretch extinguish, it causes the flame to, the stretch rate to cause extinction. Edge flames tells me what happens to that hole next. Then if I start to think about that in the context of understanding flame stabilization, as I drop equivalence ratio, the local stretch rate starts to exceed the extinction stretch rate. I get holes in the flame. Those holes in the flame will then act like edge flames. And as I keep dropping the equivalence ratio, I get more holes, and then at some point I just completely disrupt the whole recirculating flow that keeps me, that allows me to ignite ignite the flame. So what I want to talk about now is under what conditions can flames stabilize in stagnation points? So rather than in shear layers where you create flow separation, but under what conditions can they stabilize at points where the flow is aerodynamically stabilized? So let me just back you up real quick to this picture. Oh, come on. I showed you this yesterday. Remember I said that complex flows usually have multiple anchoring locations, and I showed you all these pictures. So what we were just chatting about was, well, under what conditions can it stabilize in that outer shear layer or in the shear layer on that center body, or, you know, under what conditions can it stabilize there, what conditions can it stabilize there. What I want to chat about now is, presumably if we have a swirling flow, we may have vortex breakdown, and you can have an interior stagnation point. So I could potentially, the flow could be decelerating, and I can have the conditions where a flame can stabilize aerodynamically. So let's just chat about that for a couple minutes. Oh, I had the picture here. Okay, so anyway, these are just a couple pictures of aerodynamically stabilized flames. Here's that one picture that I just talked about. But also, if the flame is only sitting in the outer shear layer, oftentimes the middle of the flame, where it will sit, will be at a point of low local flow velocity associated with the vortex breakdown bubble, as opposed to these two are sitting in shear layers. What I have here, these are some OH plinth images just showing you, these two on the left are configuration C. So it's sitting in the outer shear layer, but the middle of it, if there was no shear, this would be just a Bunsen flame, right? The whole flow would just be going down and coming back. But you see that thing sitting right there? So that part of the flame is, the reason it's where it is because presumably I have low local flow velocity. There's another time instant of an OH plinth image. Whereas these flames right here are more like configuration D. You can see they're sitting in the inner shear layer, and then they're kind of coming back around to that outer shear layer. So one of the things about when you're anchoring a flame in the interior of the flow due to swirl is, I was talking too long yesterday, I didn't have time to get into this, but swirling flows are very unsteady. And that's because you get fluid mechanic instabilities. Is when you start adding swirl, you introduce a whole menagerie of really interesting fluid mechanic instabilities that make the flow bounce up and down and sideways. They make the flow precess. So think about a top. When you spin a top, it precesses. In the same way, swirling flows precess. So what that means is the whole flow is spinning around, but the instantaneous center line of the flow is not the geometric center line, but it's off center. So the whole flow is spinning around some point that's off center, and then that point is actually precessing around. And so what that means is that when you have aerodynamically stabilized flames stabilized in the interior of the flow, that flame stabilization point is not going to be a nice, well-behaved, fixed point. In contrast, when you have shear layer stabilized flames, usually that stabilization point stays really put. It parks itself because you have a very, very well-defined flow separation point. That flow separation point is not moving much, so the flame stays pretty locked down. In contrast, the middle part of the flow is bouncing around. And I've tried to illustrate that with, this is a sequence of images from a flow and if you just look at the middle part of the flame, you'll just see it bouncing all over the place. And you can see how unsteady this thing is. So you have a flow, an annular flow that's coming out, and there it goes there, and it kind of comes out as a jet, and then it divides itself into this annular flow. You can see the jet is longer, and then it divides. See that one? See all the wrinkling on the flame? That's due to both turbulent disturbances as well as large-scale vortices. So that's what's happening. So very unsteady, but also what can also happen, as I talked about in the previous slide, is sometimes the flame will just kind of float out there in the middle if it loses the outer shear layer. But this is not always observed. Sometimes you see flames out there, sometimes you don't. But it's pretty clear that in order to have a flow that is sort of floating out there in the middle, you need to have a stagnation point in the flow. So really what this is all going to come down to is that for aerodynamically stabilized flames, you have to have a flow that stagnates, that you have to have this stagnating flow in the middle of the combustion system. And I think what I'm going to do is, I skipped over some of the swirling flow discussion before, which I kind of need here. Well, let's try it here. So, if you have a flow without a center body, you'll always have that interior stagnation flow point in a flow with breakdown. So it's very common in flows without center bodies to see an aerodynamically stabilized flame that looks like this. The problem, like I mentioned to you before, is it's also really, really hard for the flow to not make the flow just flash back, to get that combustion-induced vortex breakdown. So if you actually look out at the world today, you'll see that there's, like in flows that use swirl, there's a company called Alstom, which is a French-Swiss company that makes gas turbines. They actually do not have a center body. So they figured out the aerodynamics. Pretty much everybody else, if you look at who, Pratt & Whitney, their aircraft engines, or GE's aircraft engines, or Siemens gas turbines, or General Electric's gas turbines, or Mitsubishi Heavy Industries, they make big gas turbines. They all have a center body in the flow. And so what happens then is that when you have a swirling flow plus a center body, you can get a couple different things that are going on here. So what I'm doing is I'm showing you, this is from a Physics of Fluids paper in '96. The flow is going down, all right? And I have a center body in the flow, and the flow is swirling, and this is a smoke visualization of the recirculation zone. So what's happening is I'm moving in this direction, is I'm either increasing the swirl number or I'm increasing the center body diameter. So I could have a really slender, kind of really sharp center body, or I could have a great big bluff center body. So what you'll see is this kind of configuration, because the center body itself has flow separation behind it, right? You create a recirculation zone behind the center body. So what's happening here is well, let's just look at this one. That when you have this intermediate swirl number and center body diameter, or intermediate center body diameter, you can kind of tell that there's this recirculation zone behind the bluff body. So this is a bluff body, by the way. You can't see it. The flow's going down. But this right here is, it's kind of a little bit of a, it gives you an insight into what the recirculation zone is right behind the center body. And this is basically the wake of the center body. And then this right here is the vortex breakdown bubble. And so my point is that the wake of the center body and the vortex breakdown bubble, they can either be separate structures or they can be merged structures. So let me just jump ahead a slide. So for example, this picture right here is an image of what's happening in that previous slide. You have a wake behind the center body, you got this, and you have this region right here. And so there is actually a low velocity region in the flow that the flame could stabilize. If you start to make your center body big enough, these two structures merge, and you just get one single big recirculation zone, which is what I've drawn here. And that's what I've tried to schematically illustrate here. Okay? And so the bottom line is that this is probably a lot more fluid mechanics than many of you may have ever wanted to get into, is that the conditions under which you can get a flame that's just kind of floating out there. Who's working on a low swirl burner? There you go. The conditions under which you can get the flame just kind of floating out there is you got to have a situation where you have high velocity, which is going to not allow the flame to flash back, but also a low velocity region where the flame can stabilize. So this type of geometry would enable potentially, you could have a flame that's floating out there. This kind of geometry, either it's going to be stabilized in the inner shear layer, or you'll have nothing at all. And so this is why, if any of you, I know a number of you are working on gas turbine combustion. If you're trying to understand blowout, it can actually be quite confusing if you're looking in the literature and you're trying to compare your flame shape to somebody else's flame shape. You'll see people reporting these flame shapes, whereas you'll see other people reporting only maybe these two flame shapes before the flame blows off. And you might say, well, why doesn't it go from E to B? And it really goes back to, does the flow field allow for there to be this low velocity interior stagnation point? One last point I want to make, and then I will call it a day. is that downstream boundary conditions are really important for swirling flows. So it's easy if you're doing 1 atmosphere combustion, it's really easy to say, you know what I'm going to do? I'm going to take my swirler and I'm going to slap a quartz tube on the top of it. It'll be a foot long, and I'll take some data. I'll take some blowout data. However, the whole structure of the recirculation zone of that swirl flow, it's really sensitive to that boundary condition. So for example, this is some data from 2009 just illustrating this point. Everything's identical. This is where you have a quartz tube with no constriction, and then what they did was they put a constriction here in the quartz tube. The left shows the velocity field for that one, the right shows the velocity field for that one. Notice, for instance, that this velocity is really not going backwards in the middle. You have the flow kind of starting to turn, but you don't really get a strong recirculation zone here, whereas this one you get the flow going backwards. So just bottom line is, if you're doing blowout and swirl flows, pay attention to your boundary condition, your downstream boundary. If you have, depending upon the length of your quartz tube, depending upon the degree of contraction, you can in fact change whether you go from configuration D or E straight to blow off, or if it goes from E to B, just based upon the downstream boundary condition. Again, that might be non-intuitive, because if you were looking at a bluff body stabilized flame, you know, this flame, I mean, boundary conditions always matter. I don't mean to knock boundary conditions, but if you put this thing in a tube, I don't think the blowout limits would be that sensitive to your downstream boundary condition. The swirling it could, not necessarily, but it could really change what blowout looks like, or what your flame shapes that you see look like close to blowoff. So I just leave that as a final word of caution. I bear scars on my body from making mistakes like this. Does anyone have a question? Yeah.
So in the schematics you shown for these rollers, they've been symmetric, like perfectly symmetric. Do you observe, like, because of the PVC, some asymmetries even in the clip images?
Oh, absolutely. Yeah, absolutely. And so for example, this is a velocity field in a flow. This is the swirler. I'm showing you velocity vectors. The white line is the instantaneous recirculation zone boundary. So if you're on the inside, the flow is going down. If you're on the outside, the flow is going up. So this is a really nice, this white line is a really nice indicator of where the recirculation zone is. And this recirculating flow is precessing. It may not be obvious in this image, but you can see it's bouncing up and down. It's moving left to right. And again, this actually goes to my other point, is presumably if the leading edge of this is where the velocity is 0. So if you're downstream of that leading edge, the velocity is going up, and it'll be a very high velocity, a velocity that's close to your nozzle exit velocity, maybe 50, 100 meters per second. If you're at the white, it's 0. If you're inside the white, it's minus. So pretty significant flow deceleration that's happening. But presumably the flame is going to want to be anchoring itself right around that leading edge. But look at where that leading edge is bouncing around from this image to that image, to that image, to that image, to that image, that image. So very non-axisymmetric, and precession of the flame leading edge is very routinely observed.
Okay, so you'd see it like kind of oscillating.
Oh yeah, absolutely. Yep. Somebody have a question in the back? Yeah.
Back to your previous comment where you said boundary conditions really matter for blowout. How do you scale between a lab where you're using a cooled kind of almost adiabatic quartz tube versus a real combustor with a cooled wall with maybe something different?
Yeah, so there's a couple boundary conditions going on there. One is, I was particularly talking about exit boundary conditions. So in particular, again, boundary conditions always matter, but swirl flows post-breakdown. So pre-breakdown, like a low swirl burner, lesser so. Post-breakdown, they're very sensitive to downstream boundary conditions. I can give you, basically the technical reason for that is that you enter a regime where characteristics, well, you can even see in the flow is recirculating. But information, you get these inertial waves which can propagate upstream. So all that boundary condition information just propagates all the way back upstream. Walls, being adiabatic or non-adiabatic, that has a that can influence things like temperature of your recirculated products. But how to scale that, I wouldn't even begin to say I knew the answer to that question. But in particular, kind of making it non-adiabatic, making your recirculation zone non-adiabatic. Anyone else have a question? All right, good job. You all fought the good fight. Your brains are probably full. So have a good evening, and I'll see you tomorrow.